Hello everybody. Today we will analyze my final project for the Duke University Machine Learning for Product Manager course. In this project, we will build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. We have a set of 9,568 hourly average ambient environmental readings from sensors at the power plant, which we will use in our model. As you can see, this is the following data that we will use in our model. We will determine what type of machine learning approach is needed and select an appropriate output metric to evaluate the performance in accomplishing the task. Then, we will determine which possible features we may want to use in our model and identify the different algorithms we might consider. Furthermore, we will split our data to create a test set to evaluate the performance of our final model. Then, using my training set, I will determine a validation strategy for comparing the two models. I will therefore use my validation approach to compare at least two different models. From among the models, I will compare and I will select the model with the best performance of my validation set as my final model. I will conclude by evaluating the performance of my final model using the output metric I defined earlier. I will create two different models, A and B, to compare which model is best performing. Then I will test the model on a training set containing 80% of the data. In addition, I will test the two models on a test set containing only 20% of data to determine which model is best. Therefore, I chose Excel to try and test the different models. So we have done 6,648 observations to find the following data. So this is the data found with only 80% of the data. The R-square is of 0.9296. This represents how closely the energy outputs correlate with the environmental readings. The standard error is of 4.53. Furthermore, we can notice that the ambient pressure correlates the least with the energy outputs. Therefore, I will choose not to use the ambient pressure in the second model, B. As you can see, model A contains the following data: temperature, exhaust vacuum, ambient pressure, and relative humidity. Model B will only include temperature, exhaust vacuum, and relative humidity. Here are the results for Model A. The metric used for the validation of the models will be root square mean error, which is RMSE, mean absolute percentage error, MAPE, and mean absolute error, which is MAE. In our Model A, based on the 7,648 observations, we have found the following results: an RMSE of 5.0917, MAPE of 0.8779, and finally MAE of 4.0029. As for Model B, based on the 7,648 results, we have found the following results: an RMSE of 25.5436, MAPE of 5.4241, and finally an MAE of 24.6730. Comparing the two models, we can see that a difference of 20.526 for the RMSE, 4.526 for the MAPE, and finally 20.670 for the MAE. We can therefore conclude that the model A would be preferred. However, we will be testing the models on a test set containing only 20% of the data. So here is a Model A containing only 20% of the data. As we can see, in our Model A, based on the 1,920 observations, we have found the following results: an RMSE of 4.8509, MAPE of 0.8335, and an MAE of 3.7918. As for our Model B, Based on the 1,920 observations, we have found the following results. RMSE of 23.5503, MAPE of 4.9894, MAE of 6,462. When comparing the two models, we can see a difference of 20.6927 for the RMSE, 4.59057 for the MAPE, and 20.9712 for the MAE. These results are quite similar to the results found in the training set comparison. We can therefore conclude that Model 8 would be preferred if accuracy is the only measure of success for the model. Thank you for listening and have a wonderful day.